So, good evening, everyone. I'm Calvin Paul Joseph, and today I'll be conducting your week 8 problem solving and doubt clearing session for the course Electrical Measurements and Electronic Instrumentation, which was taught by Professor Abhishek Chatterjee. Okay. So, the outline of what I will teach today is as follows. So, today I will talk about frequency measurement, like why in a practical case we need to measure the frequency of something. I'll also consider what of a comparator of how can we use a comparator to enable us to measure frequency. Then we can use then why do we need a Schmitt trigger? Schmitt trigger is a little advanced version of a comparator where it uses a hysteresis band. So that hysteresis band is used in a Schmitt trigger to enable it to overcome the problem of noise, which can result in erroneous measurement. Okay. Also, there's a digital frequency band, like the digital frequency measurement also we will do, as well as we will see some example sums. So we'll start solving, start checking. This is week 8. So now, what do you mean by frequency? Like if we have a certain signal, okay? Like this is one signal is there. And this happens, okay? This time is like say 1 second. So can you tell me what is the frequency of the signal then? What would you say is the frequency of the signal? Like the frequency of the signal is given by the number of times it is repeated, right? So this is 1, 2, 3, 4, 5, 6. So the frequency of the signal is 6 hertz. 6 hertz, right? This is like one time period, T. This is another T. So it is repeated for 60 times in 1 second. That is why the frequency of the signal is 6 hertz. Any doubt in this part?
फिर इसके बाद मतलब इसका साइकिल फिर रिवर्स होगा क्या?
कौन सा साइकिल?
जैसे साइकिल 1 है, ठीक है, तो इसी के बाद रिपीट हो रहा है ना सर एक साइकिल?
ना, ये 1 2 मतलब हर एक सेम है। मैं सिर्फ काउंट किया ताकि आपको समझ में आए कि ये है, ये और ये सेम ही है। मतलब ये जो हुआ
अच्छा,
और ये जो हुआ सब सेम है ना। ये भी सेम है, ये भी सेम है, ये भी सेम है। मैं सिर्फ दिखा रहा हूँ कि मैं काउंट कर रहा हूँ कि 1 सेकंड में कितना बार आ रहा है। तो 1 सेकंड में जितना बार आएगा वो उसका फ्रीक्वेंसी है, होता है।
ओके सर।
तो वो ये सिग्नल का फ्रीक्वेंसी है। हाँ, तो दिस सिग्नल हैज अ फ्रीक्वेंसी ऑफ 6 हर्ट्ज। So now, how will we measure the signal? So we have studied a counter. Okay, we have studied a counter, which we used T flip-flops. Okay, T flip-flops we used and we made a counter. So a counter is basically one which will count how many times it gets triggered, how many times it gets triggered. Okay, so now this is one time it is getting triggered at the falling edge. This is the second time, this is the third time, fourth time, fifth time, sixth time. Okay, so now we have a counter and this is the clock to the counter. Okay, so the clock to the counter will be this. So at every falling edge, the counter will be here, it will be 1. Then it will become 2, then it will become 3, then become 4, then it will become 5, then it will become 6. Okay, so this is how the counter will increment. And after it becomes 6, so it becomes 6, and then we will do the counting for some particular time period. So let us check. Let us assume this is something known as your gate time. Okay, let us say this for 1 second. This is the time when your counter is active. This is the time when your counter is active. And this is your signal. Like this, your signal is coming. So at this edge, when this edge comes, your counter value will go from 0 to 1. Then the next edge comes, it will go from 1 to 2. Next edge comes, it will go from 2 to 3. Next edge comes, its value will go to 4. Okay. Next edge comes, its value will go to 5. Next edge, its value will go to 6. Next edge, its value will go to 7. So in a time period, so that means there were 7 edges in 1 second. Okay, then we know the frequency of my signal is 7 Hertz. Okay. So in this way, in some particular time frame, which we have selected, we are enabling the counter at that time, and we are counting the number of falling edges or the number of rising edges, depending on what we want to consider. Based on that, we will tell what is the frequency. So there are two conditions are there, two important conditions to realize is, first is after this time also the signal will be coming. But over here, the counter should not be enabled in this portion, that is in this region. In this region, it should be disabled. Only in this part, it should be enabled. Okay. And another aspect is, which we must understand is, that your counter should start from 0. It should not start at some other value. So we have two. So there are 2 points. One is before counting, we must reset the counter. That is one aspect. Second aspect is we must count, the counter must count only when enabled. The counter can keep on counting whenever it gets a trigger, but that will not help us to find. If we want it to count only when it is enabled, only during that time when it is enabled. Okay. So for that, what should we do is, if this is the counter, let us say this is my counter. It will first have something known as a reset signal. That reset signal must come sometime over here. Sometime a reset signal must come. And that reset signal must force my counter value to be 0. This reset signal will make sure that my counter value is 0. Okay. So that is the reset signal. Next is our actual clock. So that is a combination of an AND gate. So this is my input signal, which is just square wave. And this is the enable signal, which will be on for some time and off for the other time. So the input over here will be like this and off. So only when this enable is 1 and this is 1, then only at the output you will get 1. Otherwise, you will not get anything. Okay, so till here, are there any queries?
No, sir.
Okay. So this is how we use a counter. Next. So till now, what signal we were considering? Till now, whatever signal we were considering were digital signals. Okay, they were like these clock signals, like these signals. But if our signal is something like a sine wave, okay, or if it is a triangular wave, then what should we do? Because we cannot give an input to an AND gate of a sine wave. To an AND gate, you cannot give a sine wave. You cannot give a sine wave as an input and your enable signal like this. You cannot give a sine wave. You have to convert the sine wave into a digital wave, into a digital signal, and then you can give it as an input to your AND gate. Okay. So what will be used to convert a sine wave into a digital signal? Can anyone tell me? Okay, Schmitt trigger something. Also, we can use a comparator, a simple comparator. Okay. Yeah. So we have to use a comparator circuit. So if this is my sine wave, okay. If we have a comparator which will go high, which will be high when it is positive and low when it is negative, and again it will go high and then low, and then again it will go high. So this is the input sine wave, and this is the processed wave. Okay, this is like processed. It is being computed. Some change has been made. So if you see, this signal has a time period of t. This signal also has a time period of t. Okay. So what do we want? We want to measure the frequency. We want to measure the frequency, right? And we cannot use the original signal. So we convert the signal into a digital signal, which we can use, which has the complete information of the time period or the frequency. So our goal is to measure the frequency. And so we have converted the signal into a digital signal of the same frequency. So there is no loss till now. Okay, there's no loss, there's no error. And so then we can use a counter, enable and disable, reset, etc. to run it. Okay, but now we have got the same signal. Now, what is a comparator? How will we use a comparator is, like say this is the positive and negative terminal, and this is my input signal. This is my sine wave. Okay, and this let us connect it to the ground. And this is the plus V supply, and this is the minus V supply. And this is my output. So whenever my input becomes more than then the positive is higher than the negative terminal, then the comparator's output will go high. Okay, because the gain of the op-amp is very high. Gain of op-amp is very, very high. Very high. Okay. So that is why whenever Vp is greater than Vn, output will go to plus V supply. And whenever your Vp is less than Vn, your output will be equal to minus V supply. Okay, so this is like a comparator, and we are working. So there is no problem. There is no issue. Okay, we are able to get the same frequency at the output, and we can be happy. But then why did we go for a Schmitt trigger then? Why did we have to use a Schmitt trigger circuit then? why a comparator circuit is not enough. Niranjan, NS. Yes. Noise is an issue. So we have to use what is known as a Schmitt trigger. So if this is our signal, okay, this is our signal, it is going like this. And then we convert it to high, low, high, low, high, low, etc. But if there is noise in my signal, there's some noise. Okay, there is some sort of noise. Then what will happen is, it will become a signal which was going like this. Let us say this is what's going like this. It was coming over here somewhere. It becomes negative. Then again it goes above. So again it becomes positive. Again it will go down. Again it will be negative. Similarly over here, let us assume this goes very high. This goes like this. Then what will happen to my signal? At this point it will go positive. Again it will go negative. Again it will go positive and remain positive. Okay, so there is more peaks. So and if we are count, what do we count? We count the falling edges. This edge and this edge. So here there will be one falling edge, one falling edge, one more falling edge. So instead of there being only one, we are two, we are getting in that same time. Over here also it will fall. Here it might fall worst itself. So it may fall off here and it may again rise, again fall. So 1, 2. So in original signal, there were 2 falling edges. But in what we got, we are getting 5 falling edges. So then when we are using these falling edges to measure what is known as the frequency, we will get an error. Okay, an error will be there. So what is done is, they use a band. This is not seen. They use what is known as a band. So only when my signal goes above this band, then only it will become positive. Okay. So let us say once it goes above this band, it becomes positive. And even if it goes below the band, it will not become a 0. Only if it goes below this lower band, there's the upper band and the lower band. So if it goes above the upper band, it will become positive. And it will remain positive until the signal goes below the lower band. So it will not go. So over here also, it will not create an issue. It will, even if it goes below 0, it will still be high. It will go on, your signal will go on like that. Signal will continue. Okay, it is keeping on, going on, going on. Only when it goes below this band, what will happen is your signal will go negative. And even though the signal goes high, goes above 0 over here, it has not gone above your upper band. So it will still not go high and low again. It will still remain low. So it will continue like this. And over here, it will go high. And still when it falls lower also, it is not going below the lower band. So it will still remain high. Okay. So in this manner, we are getting a signal which has one edge over here, one edge over here. This signal also has 2 edges. So even though there is noise, it has the same frequency as your original signal. And this is because of these bands. These bands are preventing it from changing state, from being very sensitive. Okay, only if it crosses a large value, deviates, then only it is changing. Okay, so there's some sort of protection, there's certain margin is present. Okay. So any questions in this? Okay. So now we understood this. So let us look at a circuit. So we understood what is the purpose of Schmitt trigger. Now we have to look at the Schmitt trigger circuit. So as Sir taught, let us consider an inverting amplifier, right? This is connected to ground. This is my R1. This is my R2. My V out. This is my V in, right? So in this connection, it is an inverting amplifier, which is V output is equal to minus V in into R2 by R1. But Sir said, what will happen is if we change these terminals, this becomes positive, this becomes negative, right? So then it becomes positive feedback. It becomes known as positive feedback. So what happens in positive feedback? Your output is being fed to the positive thing. So if your V output will increase, over here also there is an increase. So your VP is increased, but your VN is still equal to 0. So VP increases, what will happen? Your V output will increase further. Okay. So in this way, when there's a small increase in V output, that goes and increases VP. VP will increase further, will increase, and so your V output will increase more. So it is like a avalanche. It is like a continuous increase will happen until it will saturate at your plus V supply or at your minus V supply. Similarly, if your V output goes low, then your VP will also go low. And then what will happen? Your VP is lower, but your VN is at the same. So then your V output will further reduce. It will further reduce. It will further go down until it will reach minus V supply. Okay, it's something like this. So this is the concept of positive feedback. Now, how do we ensure that there's a certain band? Okay, one band is there, which will sort of, help in protection, help in overcoming the problem of noise. So we have, so what is the potential over here? What is VP over here? Let us derive it. So we know no current will flow into the terminals of the op-amp. And we cannot consider here virtual short. Virtual short is not valid because there is positive feedback. If there's negative feedback, we can consider the concept of virtual short. But in this circuit, it is not valid. So what should we do then? We have to, suppose there's some current here, Ix. No current goes here, so the same current goes here, that is Ix. So what is this Ix? Ix is equal to Vin minus Vp by R1, which is equal to Vp minus V output by R2, right? So we have V in upon R1 plus V output upon R2 is equal to Vp upon R1 plus Vp upon R2. So this is V in into R2 plus V output into R1 upon R1 into R2, which is equal to Vp into R1 plus R2 upon R1 into R2. So we can cancel these. We cancel. So we get Vp is equal to V in into R2 by R1 plus R2 plus V output into R1 upon R1 plus R2. Right. So this is the equation of Vp. Now, so actually this expression I derived because like sir was just considering it and writing it, but I just sort of derived it so you know why is this expression there, how it is an average of the input and the output voltage. Okay, that's why I sort of derived it for you guys to know how is sir directly writing this expression. So now we will assume. So we first, because of positive feedback, we know this has only two possible outputs. There are two outputs. It can either be plus V supply or minus V supply. Only these are your possible outputs of this circuit. So we know that there are two possible things. So let us assume your V output is plus V supply. Another thing to remember is your Vn is 0. Your Vn is 0. So your V output is plus V supply. If your V output is plus V supply, what does it mean? Your Vp is greater than Vn. If your Vp is greater than Vn, then your V output is plus V supply. Okay. So what is your Vp in this case? Your Vp is equal to Vn into R2 by R1 plus R2, and V output is plus V supply. So V supply into R1 upon R1 plus R2. Now what do we want? We want to know when V output will go from plus V supply to minus V supply. So what should happen then? In that case, what will happen? Your Vp should be less than Vn for that to happen. Then what you should consider? That means your Vn into R2 by R1 plus R2 plus V supply into R1 by R1 plus R2 should be less than Vn, should be less than 0. For that to happen, what should happen? See, this R1 plus R2 and R1 plus R2, it becomes 0. So it should mean your Vn into R2 should be less than V supply into R1. That means your Vn should be less than V supply into R1 by R2. So if your Vn goes below V supply into R1 plus by R2, then what will happen? Your output will become minus V supply. Okay. Now, this is how, at what condition your output will change. We will derive another condition also for the next case. And then I will draw a kind of, what you say, diagram so you'll understand it. Okay, waveform. Now we know, what do we know? Your Vp is equal to Vn into R2 by R1 plus R2 plus V output into R1 by R1 plus R2. Now we know, let us assume my V output is equal to minus V supply, right? So that means what was the case? It was a case when Vp is less than Vn, right? So now, what is happening is my Vn into R2 by R1 plus R2, this is my Vp. And then because V output is minus V supply, it is minus V supply into R1 by R1 plus R2. Now what do we want? My V output should go from minus V supply to plus V supply. For that to happen, what would happen? My Vp should become greater than Vn, right? If my Vp must be greater than Vn, that means my Vn into R2 by R1 plus R2 minus V supply into R1 upon R1 plus R2 must become greater than 0. Right? So that means V in into R2 should be greater than V supply into R1, or V in must be greater than V supply into R1 by R2. Have I made any mistake? Because I got the same condition for both. Should not be the case. Okay, I made a mistake. In the first case. So what I forgot to see is this is V into R2 plus V supply into R1, right? This is R1. So now when it goes here, it becomes minus. Plus is here, it goes here, it becomes minus. So this will be minus V supply into R1 by R2. Okay, so this is the mistake I made. So this plus, when it goes here, it becomes minus. So it becomes minus V supply into R1. So when V in becomes less than minus V supply into R1 by R2, then my V output will become minus V supply. Over here, we have derived when V in becomes greater than V supply into R1 by R2, my V output will go from minus V supply to plus V supply. So let us draw some curves. Let us draw the points. So this is my V supply into R1 by R2. And this is my minus V supply into R1 by R2. Okay. So what do we know? And what will be my V output? What will be my this should be my V output. Okay. So we assume, let's assume my V output was positive. Let's assume it was positive. Okay, and we saw that when my V in becomes greater than V supply by R1 by R2, then it becomes positive. Okay. So we'll consider this case. My V output was minus V supply. Okay. When my input, this is my input. When my input becomes greater than this V supply into R1 by R2, it will become positive. Okay, so then my output will go from minus V supply to plus V supply. Okay. And it will go on. Even if it crosses 0, it will still be positive. And only when my V output becomes less than minus V supply R1 by R2, it will go low. Okay. Then it is still low, so it will continue. And then when it crosses this point also, it will still remain low. When it crosses 0 also, it will still remain low. Only once when it crosses this point, and it becomes higher than V supply by R1 by R2, then it will go high. And it will remain high. When it falls below this also, it still remains high. Below this also, it remains high. Once it goes below this, then it will go low. Okay, so this is how there is a band in which we are able to make it change. When it will change, when it will go high, when it will go low. So in a comparator case, there's only one voltage, which will decide whether it will go high or low depending on this voltage. But here there are two voltages. This will decide when it will go high, and this will decide when it will go low. And this is known as your hysteresis band. This is known as your band. This is known as your upper trigger point. This is known as your lower trigger point. Okay. So This meeting will end in 1 minute. After that, I will restart this meeting. So then you can join with the same link. Okay. Thank you. So this is actually a non-inverting. This is a non-inverting Schmitt trigger. Like your output is changing when your input is increasing. Because your output is going positive when your input is going positive. Your output becomes negative when your input is reducing. So that's why it is a non-inverting. Depending on how your rate at which your output is, whether your input is increasing, then at some condition it becomes positive. When your input is reducing, then at some condition it will become negative. So that is why it is a non-inverting Schmitt trigger. There's another circuit in which it happens opposite. That when your input is increasing, your output suddenly becomes zero, it falls low. And when your input is reducing, then your output goes high. Okay, so that is an inverting Schmitt trigger. So now let me ask you a question. At this point, let us say at this point, let us say it is like 1 volt. Okay. So when my input is equal to 1 volt, what is my output? Can anyone tell me? When my input is 1 volt, what is my output? Well, first we'll start with the simpler one. Let us say my input is, let us say, 5 volt. Okay, let us say this is 2.5, this is minus 2.5 volt, etc. So when my V input was 5 volt, my output will be plus V supply. It has to be plus V supply. When my input is more negative or minus 2.5 volt, it has to be minus V supply. But when my V input is 1 volt, that is, it is within this band, then my output will depend on what was the previous output. Okay. It depends. If my output was positive, that is over here, what is this? My output is positive plus V supply. So it will still remain positive. Over here, what happens? My output was minus V supply. So it will still remain minus V supply. Okay. So it is not like at one input voltage, there's a unique output voltage. When it is within that band, your, your input voltage will depend on, your output voltage will depend on the previous output. Okay. So there's something known as a history term. What was the previous? It is having the memory of that. And depending on that, it is giving the output. Okay. So that is the logic which is there in this circuit. So let us draw the characteristics of the Schmitt trigger. We'll draw them. This is my input. This is my output. Let us say this is the plus V supply. This is the minus V supply. This is one band. V supply into R1 by R2. This is minus V supply into R1 by R2. So this is the upper trigger point, this is the lower trigger point. Let us say, like when we consider sine wave, my output was minus V supply. And my input is increasing, still it is still minus V supply. Once it crosses this, it will go high. When my input is increasing, it will keep on, it will still remain at plus V supply because it cannot go above it. Then let us say it reaches its maximum value. So it is going like this. Then my input will start reducing. Still it will be positive. Starts reducing. Still it will be positive. It goes below this point also. Still it will be positive. Okay, let us make this like this. Still it will be positive. Then once it goes minus V supply R1 by R2, then it will go negative. Then it will go negative. And then the input is still becoming negative. It will still remain at minus V supply. So it goes like this, goes like this, goes like this. Then again it will go like this. It will go like this. So this is similar to what is known as your BH curve. BH curve, there's more of a curve in the BH curve. This is more of a very squarish rectangular one. BH curve is kind of different, but it has history and it has a band. Okay. So these are characteristics of the Schmitt trigger. So any queries in this regarding the characteristics of the Schmitt trigger? Okay. So let us see this. Let us first see this. Okay. So your input, your output was negative, right? Your output was negative. And your input was increasing. So your input is increasing from here to here. But your output is also still negative. So let us come back over here. Let us say your input was 0, right? Now your input is increasing, but your output will still be negative. Your output is still negative. Then your input goes above this band, above this V supply R1 by R2. It goes above. As soon as it goes above, what happens to your output? Your output becomes positive. So what has happened? Your input has gone more than this. So your output has gone positive, and your input is still increasing, but your output can remain only at plus V supply. So it comes to, let us say, the maximum of your input voltage. So let us say it has reached till here. Okay, at this point, at this maximum, it has reached. Now what happens is your input is reducing. It is reducing. And then it reaches this upper trigger point. So it is reducing. Okay, it is reducing. And it reaches this point also. Still your output will be positive. Then your input will reduce. Still it touches 0. So your input reduces, touches 0. Still your output is plus V supply. Then your input reduces, touches this point. Then your output will become minus V supply. So what is happening? It is reducing. It touches this point. Then your output becomes negative. Once your output has become negative over here, then your input is further reducing, but your output is stuck at its most minimum value, minus V supply. Your input reaches its most negative value. So it goes on over here, up to this most negative value. But your output will still remain at minus V supply because this is your output, this is your input, right? Next, what happens? Your input starts increasing. It touches this, still your output will be negative. You go on increasing, touches 0, still it will be negative. You go above this band, then it will change. So how do we represent that? We come back like this over here. We touch this point, no change, it will still be negative. We touch 0, no change, still it will be negative. We touch this top upper trigger point, then it becomes plus V supply. So that is how the characteristics of the Schmitt trigger are represented in this input-output characteristics of the Schmitt trigger. Okay. Okay. Thank you. So now we will see frequency measurement. So we have seen if your signal is a digital signal, we are able to measure its frequency. If it is not a digital signal, we use a comparator or we use a Schmitt trigger, and then we can get a digital signal which can be used to measure the frequency. So what do we do in frequency measurement? We have some time period, which is known as my gate time. Okay. This is my enable signal sort of for my counter. We have a counter. Okay. And we have an input digital signal. If it was an analog or a sine wave or some other way, we convert it into a digital signal. Right? Now, we have a counter. Its value could be anything. Earlier, its value could be anything, x, some value. But before, let's say we have a reset. Before we start the gate time, we have to make sure the value becomes 0. So we give some reset signal and my counter value be 0. Okay. Let us say our input signal is something, we don't mind. Then it gets enabled. Okay. And then the signal comes like this. My input signal keeps coming like this. Okay. It is not of the same frequency as shown because my diagram is not good, but you must understand. So now what happens is, let us say at the falling edge, it is counting. So it is 0 now. Now it becomes 1, then becomes, so over here, it will be, sorry. This having value 0, will be 0 still. Then it will become 1. Then it will become 2. Then at the next falling edge, it will become 3. Next falling edge, it will become 4. Next falling edge, it will become 5. Next falling edge, it will become 6. And so on, it will go. So on, it will count. This is how my counter will count. So I have a signal of some particular frequency. Let I give some gate time. I give some gate time of 1 second or something. So what will be the value at the end? Let us say the value at the end is, let us say 20. Okay. So my counter value is 20 at the end. Then I will say the frequency of my signal is 20 hertz. Okay. It is 20 hertz. Something like this. Okay. Now what will happen is, suppose the signal was shifted a bit. The falling edge came somewhere here. So there could be a condition, like it actually varies very, let me draw one more thing so it'll be more understandable. Let us say this is my enable thing. And in one case, I have a signal which is starting exactly like this. Okay, exactly like this. Let us say we have a signal which is like this. Okay. So now, if this is the gate time, I'm getting 1, 2, 3, 4, 5, 6. I'm getting a count of 6, right? Suppose my gate time is 1 second. This is 6 hertz. But what if there is a shift? What if there is some slight shift? What if it had a signal which was, let us say, like this. 1, 2, right? 3. So at this instant, after that, slowly there's been an edge. 4, 5, 6, 7, and go. So you will get a count of 7 hertz here. Okay, you will get a count of 7 hertz. Okay, so one thing to note is this will not be like this. This has to be something like this. A signal has to go high here. Okay, something like this. So you're getting a count of 6 hertz here, you're getting a count of 7 hertz here. But what you may miss out is your actual original signal was 6.5 hertz. Your original signal is 6.5 hertz, but the signal you're measuring is either 6 hertz or 7 hertz. So there is what error is there? There's an error of count error of 1. Maximum count error can be 1. It can either be 6 or it could be 7, right? So there is a count error of 1. There's a mismatch of 1. So this is a problem. So what should we do in case, how do we make sure this error is less or reduced or negligible is, we must increase the gate time. If we increase the gate time, what will happen? The measurement will be more accurate. Okay, measurement will be more accurate. But can anyone tell me what will be the problem if we increase the gate time to be very high? Like what can be an issue you may face? Can anyone tell? Hmm? What will happen if I increase the gate time a lot, make it too high? If I say you measure for 1 minute, you measure how many times it is happening. You make the gate time of 1 minute. Then the time which you're taking to measure the frequency is like 1 minute, which is very high. You saw for 1 second, you're getting some error. So what you do, you tell, okay, you increase it. You make the horizon or the gate time to be very high, 1 minute, let us say. Then you will wait for 1 minute. Then you have to see what is the counter value. And then you may have to do some pre-process, some post-processing something. And then you will see the output showing that, yes, the frequency is 6.5 hertz, but that is taking a lot of time. And we don't always have that much time. And nowadays, what we want a computer, we want our processor, we want everything to work very fast. And then if we use this crude, this old method or brute force method to get accuracy, but the time is lost. So this is not acceptable. So there's a new way. There's a way, alternative approach, which we can use to count the frequency. So what is done is we go for something known as reciprocal counting. What I can do is, if this is my signal, okay, let us, this is too small. If this is my signal, okay, this time itself is 1 second. This time is another 1 second. Assume something like this. Okay, so the time is very large. So that means my frequency of my signal is 0.5 hertz because the time period is 2 seconds. Okay. So this time is very large and I cannot afford to waste so much of time, spend so much of time, etc. So then what will happen is if I do direct counting, then I'll have to make my gate time to be very high. It will have to be very high. But then I cannot do that. So this is my input signal. What I do, I give my reference signal. I give a reference signal of very high frequency. So now in this band, I will count the number of falling edges. within this time, half of the input signal time period, I will count the number of falling edges. Let us say the number of falling edges, let us say the number of falling edges is 12. Okay, it is 12. The number is 12. So, okay, let us use an easier number. Let us assume the count is 10. Okay, the count is 10. And we know that this reference signal has a frequency of 10 hertz. So, if in the time when this is high, we are getting a count of 10, that means our signal frequency is 10, is like my count divided by the reference signal frequency. So that is equal to 10 upon 10. So our signal frequency is 1 hertz. Okay, so our signal frequency is 1 hertz. Okay, there's a mistake. So because it is of the 0.5, so it will be actually count divided 2 into reference signal frequency. So 2 into 10, so 1 upon 2, so that is 0.5 hertz. Okay, so in that way, within 1 second, so using this method, the time to get frequency measurement is 1 second. But if we use the other method, we'd have to wait like around 10 seconds or something. So we are sort of reducing the amount of time it is taking for us to get the frequency measurement. Okay. So is there any confusion in this? Any doubt in this method of reciprocal counting? Hmm? Okay. So if there are no doubts, we can start with the questions. So, just 1 minute. So let us see this question, okay? This is the circuit. Take a snip of it. So we have to find the hysteresis band. Anything else? Okay, we have to just find the hysteresis band. So when you see this circuit in the exam, you will not know that it is a Schmitt trigger circuit or something like that, because you have studied so many topics, so many things you have learned. When you see op-amp, it could be an inverting, non-inverting amplifier, it could be a comparator, it could be a Schmitt trigger. What is the circuit? How will you identify? Can you apply virtual short ground concept over here or not? First thing you see, what is the feedback? Here, if you see, it is positive feedback, right? You see it is positive feedback. So you know you cannot apply the virtual short ground concept. And they have told told hysteresis band, so you know that it is a Schmitt trigger. So those things are confirmed, like you're confirming what you think. So when you solve, you might get some idea, and then you must see that what you're solving is like supporting what you thought earlier, right? To verify that you thought or understood correctly. Okay, so now we know that it is positive feedback, hysteresis band, so it is a Schmitt trigger circuit. Now what I do is, I will name, let us say my 1 kilo ohm, I name it R1, this I name it R2, this also I name it R1, this also I name it R2. So what I will get is like a sort of generalized expression. I prefer doing this because it will help me to understand the circuit, everything, as well as in case there's some error in some value which I take, it will not create, it will be easier to back calculate and check again. Okay, so that's why I prefer doing labeling the resistors. It makes it easier for me. Now, this is the point Vn, this is the point Vp. Okay, we have got Vn and Vp. Now we must find out this thing. So what I will do is I will label this point as my Vin positive, and this is a point at Vin minus negative. So this point is at a potential of Vn positive. This point is at a potential of Vn negative. So what is my Vn? My Vn is Vn positive into this R2 by R1 plus R2. Okay. Any doubts in this? How did I get my Vn? So this current here is 0. So all the current must go here. So my Vn is Vn positive into R2 by R1 plus R2. So if there are no questions, I'll proceed. Okay. So now there's some current flowing here, and there's some current flowing here. And this current is 0. So these currents, let us say some Ix, they should be same. So my Ix is what? My Vin minus my Vp by R1 is equal to my Vp minus V output by R2. Right? And if you simplify, you will get this expression. My Vin minus is equal to my, okay, sorry, your Vp is equal to Vin minus into R2 plus V output into R1 by R1 into R2. Let me check again. I'm having some. Let us derive it properly. Verify. So I have Vin minus upon R1 plus V output by R2 is equal to Vp upon R1 plus Vp upon R2. So Vin minus into R2 plus V output upon into R1 upon R1 into R2 is Vp into R1 plus R2 upon R1 into R2. So this is my Vp is equal to Vin minus R2 plus V output into R1 by R1 plus R2. Okay. So we got this expression. So now we have to see what is Vp minus Vn. What is Vp minus Vn? This is Vn minus into R2 by R1 plus R2 plus V output into R1 by R1 plus R2 minus your Vn is Vn plus into R2 by R1 plus R2. So your Vp minus Vn is equal to V output into R1 by R1 plus R2 minus of V input plus minus V input minus into R2 upon R1 plus R2. So this is Vp minus Vn is equal to V output R1 by R1 plus R2 minus your Vn into R2 by R1 plus R2. Okay. So I've got the expression of Vp minus Vn. Now, there are two conditions. What are the two conditions? You have to find you assume your V output was equal to plus V supply. Okay. Now you want it to become minus V supply. If it has to become minus V supply, what should happen? Your Vp minus Vn should become less than 0. Okay. So that means Vp minus Vn should be less than 0. That means your V supply into R1 by R1 plus R2 minus V input into R2 by R1 plus R2 should become less than 0. What does that mean? Your V supply into R1 should be less than V input into R2. That means your V input must be greater than V supply into R1 by R2. So this is your first case or your first point. Next, in second condition, your V output now was minus V supply, and you want to change it to plus V supply. For this to happen, what should happen? Your Vp minus Vn must become greater than 0. That means your minus V supply into R1 by R1 plus R2 minus V input into R2 by R1 plus R2 must be greater than 0. So what it means? Your minus V supply R1 must be greater than V into R2, right? So your V in must be less than minus V supply into R1 by R2. If this happens, your output will go from minus V supply to plus V supply. So this actually is a non-inverting, this actually is an inverting Schmitt trigger. This is an inverting Schmitt trigger. This is your second point. Okay. So in this circuit, what actually happens is minus V supply into R1 by R2. This is your V output. So when your V input will become greater than V supply into R1 by R2, your output will become negative. So earlier your output was positive, then it will go negative, and then when it crosses this point, then it will go positive. Then it will keep on being positive, then when it crosses this point, then it will become negative. So it is sort of opposite. When your input is increasing, your output is reducing. That's why it is known as an inverting Schmitt trigger. So what is this band? Your hysteresis band is 2 into your V supply into R1 by R2. This is your band, right? So what is your R1 and V supply in this? So your R1 is 1 kilo ohm, your R2 is 6 kilo ohm, your V supply is 12 volt. Okay. So we have your band is equal to, your band is equal to 2 into 12 into 1K upon 6K, that is equal to 24 upon 6, which is equal to 4 volt. Okay, so this is your band. So any questions on this? Okay. So we'll proceed to the next sum. So now, so first we must note down it is reciprocal. Okay, it is a reciprocal counting method. It is used to measure frequency of an unknown periodic signal. The clock frequency is 10 kilohertz. Now the counter value is 1461. Okay. So now we have a 10 kilohertz signal. Okay, this is my clock of 10 kilohertz. Okay, it is coming regularly. It's coming. Now we have a reciprocal counting method. The reciprocal counting method, we will have a gate time. Okay, this is my gate. This is the signal, actual signal, digital signal of that, of my input signal, and this is my gate time. My gate time is the same time as the time period of my signal. And how many edges come, that my counter will count. So my counter has counted 1461 edges, and the clock is 10 kilohertz. So what is the frequency of my signal? So the time is equal to what? Your 10 kilohertz into 1461, right? This is counting 1461 signals. No, your time can't be 14. Okay, sorry. So this should be time period, be the number of counts or the value of your counter upon your clock frequency. So that is 1461 upon your 10 kilohertz. So that is 10 into 10 to the power 3. So that is your time period is 0.1461 seconds. So what is your frequency then? Frequency is 1 upon t. So what is 1 upon 0.1461? It is 6.84. Okay. Okay, it is 6.84 hertz. So now we got the frequency of my signal 6.84 hertz, and we have used this reciprocal counting method. We'll go to the next question. So they are saying to snippet. they're saying the time period of a periodic signal is about a few seconds. To measure the frequency of the signal with a digital frequency meter, which mode is more suitable? Should I go for the reciprocal counting mode or should I go for the direct counting mode? Okay, so which mode would you guys say I should proceed with? So we must go with the reciprocal counting mode, because if you go with the direct counting mode, we have to give a large gate time. The gate time will be like 100 seconds, something like that, which is too much time. Okay. But then if there's an easier alternative, smaller method or a shorter time period in which we can compute, faster method, then we will go for that. So that is the reciprocal counting method, which is an actual thing. So this one, why did we do? Because the frequency of a signal was 6.84 hertz, right? So its time period was like 0.1461 seconds. In this case, in the next question, the time period is like about a few seconds, more than that. Okay, so that's why the power, which a reciprocal counting mode will be seen, it can be understood like from this question, previous question. Okay. So now we will go to the next question. So we have a signal of frequency 33 hertz. So my method when I solve sums is I write down whatever information is given, so that I don't need to recheck the question again. Okay, so I write it down. This I find it to be useful for me. So I have to find frequency is 33 hertz. I am going to use a digital frequency meter, and the gate time is 500 milliseconds. So I prefer to convert it all in terms of seconds. I make it 0.5 seconds. Okay. Now they are told it is a direct counting method. Direct counting mode. So how much error can occur? That we have to see. So my counter will increment every falling edge or rising edge, whatever, some edge, right? So my signal is coming like this, like that. Every edge, it will count. And this is like, say, my time. Time they have given is 0.5 seconds. Okay. So how many edges it can count? Now the frequency of the signal is 33 hertz. So at around 33 hertz, in 1 second, 33 hertz will come. So in 0.5 seconds, it should come 16.5 counts, it should count. But my counter will count, it should actually count. What a true counter would count like say 0.5 into 33 hertz. That will come out to be 16.5. So this should be my true count. But my counter cannot count fractions. It counts only integers. It can count 0, 1, 2, 3. It cannot count 0.1, 0.2, 0.3, 1.1. It cannot do that. 1.5 cannot do that. So my counter will either show 16 or 17. That depends on where the edge comes. If the edge is coming here, or the edge comes here, the edge comes here, or the edge comes here, it depends on that. So it can count either 16 or 17. So by my true count, the frequency is 33 hertz. But for my counter, what frequency I will get? If it is counter is showing 16, that means I will get frequency of 32 hertz or 34 hertz. Okay. So in both cases, my error is like -1 hertz or +1 hertz. Okay. So we are told to find the percentage relative error, right? And note it down very carefully. that they have to enter as a positive number. So what it should be just a positive number. So we will take mod of the frequency error by the true frequency into 100. So that is 1 upon 33 into 100. That is 3.03%. Okay. So do you have any queries in this? Okay. So there's direct counting mode. So that means we have some gate time of 0.5 seconds. And there's a frequency, input frequency of 33 hertz. So my counter, like the true count, it should give us 0.5 into 33. 0.5 seconds into 33 hertz will show 16.5. That should be my true count. But my counter can count only 0, 1, 2, 3, 4. Right? So it will count 16 or 17. 16.5 hertz, 16.5 corresponds to 33 hertz. But 16 or 17 corresponds to 32 hertz or 34 hertz. So the frequency is either, but the original frequency is 33 hertz. So the error, frequency error is like either -1 hertz or +1 hertz. So the percentage relative error is the frequency error. I'm taking the absolute value of the frequency error divided by the true frequency into 100. So that is 1 upon 33 into 100. So it becomes 3.03%. Okay. Okay, thank you. So now we will proceed further. So network. Sorry. So this is a question. Okay. So what have they asked? They have asked the upper trigger point, lower trigger point, and the hysteresis band. So first, again, let us see this is positive feedback. So it's a Schmitt trigger, and they are telling you to find the upper trigger point, the lower trigger point, and the band. So these are what we have to find. So first, we have to have, this is my VN, this is my VP. Current over here is 0. So this is the current which will flow IX. Same current IX will flow. So what is my IX? My IX is equal to, IX will have many ways we can write IX. My IX, I can find it is my V output minus 5, there is 5 volt, by the total resistance 10K. This is one value of IX. I can also write IX to be equal to V output minus VP upon 8K. From here to here, if I consider, then it is V output minus VP upon 8K. If I consider from here to here, then V output minus 5 upon 10K. Or it could be VP minus 5 upon 2K. Both, that is, I'm considering from here to here. So there are 3 cases I can consider, and I'm going to get the same value of my current IX. So this I have found out. Now, what I want is an expression of VP in terms of V output. So what I will do, I want to find an expression of VP in terms of V output. So I will use these two expressions. Okay. So I have V output minus VP upon 8K is equal to VP minus 5 upon 2K. K and K gets cut, 2 and this becomes 4. So you get V output minus VP upon 4 is equal to VP minus 5. So V output minus VP is equal to 4 VP minus 20, right? So your V output plus 20 is equal to 5 VP. So your VP is equal to V output upon 5 plus 4. Okay, this is the expression of VP. Then my Vn is equal to my Vin. My Vn is equal to Vin. Now we want to find, we have to have two cases. Let us see for the, first of all, this is a inverting Schmitt trigger, so it's a more tricky. So we have case 1. My V output is equal to minus V supply. V output is equal to V output is equal to plus V supply. I want it to become minus V supply. That means what? My VP should become less than Vn, right? So that means my V output by 5 plus 4 must be less than my V in. My V output is plus V supply, so V supply upon 5 plus 4 should be less than my V in, right? So my V supply is 12. So my 12 by 5 plus 4 should be less than my V in. So when my V in becomes greater than 12 by 5 plus 4, what is 12 by 5 plus 4? When my V in becomes greater than 6.5 volt, then it will go from plus V supply to minus V supply. So this is my lower trigger point. Okay, when it goes from plus V supply to minus V supply, so this is 6.54 volt. Now we will consider the next case. When it goes from minus V supply to plus V supply. In that case, what do we want? In that case, we want my VP to be greater than Vn. So what is my VP? That is V output by 4 plus 5 is greater than Vin. So what was my V output minus V supply? So it is minus 12 by 4 plus 5 is greater than Vin. So your Vin is less than minus, sorry, actually, this is 12 by 5 plus 4. Vn should become minus 2.5 plus 4. So Vn should be less than 1.6 volt. So this is my, okay, this is my upper trigger point where it is the higher volt value. And this is my lower trigger point. So my lower trigger point is 1.6 volt. Okay. So now my band is the difference between my upper trigger point minus my lower trigger point. That is 6.4 minus 1.6. So how much is this value? So this is 4.8 volt. Correct. Okay. So that is how we have got our answer. Now let us proceed this question. Let us say this is my R1, this is my R2. Okay. Again, they've used 12 volt and minus 12 volt, so our V supply is fixed. We know one thing, that our V, this is my VP, this is my VN. My VN is 2 volt, fixed. What is my VP? VP, if you guys will know, we have done it, we have proved it. It is VN into R2 plus V output into R1 by R1 plus R2. Okay, this is the expression. So now we want to find, what have they asked? They have asked us, sorry, they have asked us upper trigger point, lower trigger point, and hysteresis band. Fine. The same thing which we did earlier. So what we have to do is, we have to find the condition when it goes from plus V supply to minus V supply. In that case, what happens? Your VP must become less than VN. VN. In that case, this is VN R2 plus V output R1 upon R1 plus R2 should be less than VN, which is 2 volt. Right? So your VN R2 is what? 32K. V output was how much? V output was plus V supply. So your plus V supply means 12 into R1 is what? 4K upon 36K should be less than 2. So your K and K get cancelled. So V input into 32 plus 48 should be less than 2 into 36, that is 72. Okay. So V input into 32 should be less than 72 minus 48 is how much? Is 24. Right? So my V input should be less than 24 upon 32, which is equal to 0.75 volt. So this is my first trigger point. Okay. Now we'll consider a case when my output was minus V supply, then it goes to plus V supply. So that means it is going to positive. So that means my VP should be greater than VN, right? So it is VN into R2 plus V output into R1 by R1 plus R2 should be greater than 2. So your VN into 32K plus V output was minus V supply, so minus 12 into 4K upon 36K should be greater than 2. So you K and K get cancelled again. So V input into 32 minus 48 should be greater than 72. So V input into 32 should be greater than 48 plus 72 is 120. So V input should be greater than 120 by 32, which is equal to 60 by 16, 30 by 8, 15 by 4, 3.75. Yes, 3.75 volt. So this is my upper trigger point is 3.75 volt. My lower trigger point is 0.75 volt. And my band is equal to my upper trigger point minus my lower trigger point, that is equal to 3 volt. Okay. So Okay. So now I actually thought of doing something different today. Just wanted to show, okay, something new. Let me open there's a LTSpice model which I made. Okay. So LTSpice is a free software which we can use to simulate our circuits. Okay. Uh, this is a newest version which I downloaded recently. So it looks a bit better than the old LTSpice versions. And this is a very, very popular software, etc. This is like provided by some analog devices, some company. So in all these circuits, I use a plus 12 volt, I use a minus 12 volt, right? And I label it as plus V supply, minus V supply. So what I do over here is I give a 12 volt, I give a DC voltage source, value is 12 volt, and I label it as, and I give that point to be plus V supply with respect to the ground of my circuit. Then I have another DC voltage source, which I give it minus 12 volt with respect to the ground, and that is again minus V supply. That is minus V supply now. Now I come to my op-amp. This is my op-amp. This is the negative terminal, this is the positive terminal. This is my plus V supply, which comes over here, the positive terminal to the positive supply terminal. Minus V supply point comes to the negative terminal. So that means this point and this point are the same point. They are connected. Okay, so that it will look neat, I use this thing. So these are known as node points. These are known as net point or label net. Okay, it's known as a net. Now, I have connected the output to some resistor, load resistor, it's fine. This is my R2, this is my R1. And I'm using an inverting Schmitt trigger. So that means it is going to the negative terminal. Okay. My input is a sine wave. We will look into it. I will show it. I will show it. So this is my circuit. Okay, I have made my circuit in LTSpice and I have considered it will run as a transient simulation. Transient is like a time simulation, which will run for some time. So it will run for 10 milliseconds and will start from 0 second and it will go at a time step, 0.1 microsecond it will use to do the calculation. Okay, so these are some things. So when you use this software, probably you have used it or you may not have used it till now, but this is a very useful software. It's a free software. That's why it is very popular. Now let me run it. So I run it. Okay. So I'm seeing. So the green one is my output. Blue one is my input. So let me first delete my, let us see my input. What is my input? If you see, it is going maximum to around 9 volt. Okay, maximum around 9 volt. Minimum around minus 7 volt, right? So it has a DC offset of 1 volt. Okay, so this is my input voltage. This is my input sine wave. And since this is an inverting one, the trigger point, that is the trigger point, that is the trigger point will be given by V supply into R1 by R1 plus R2. So that is 12 into R1 is 10K, R1 plus R2 is 10K plus 10K. So it is like around 6 volt. So at plus 6 volt, it will get triggered. And at minus 6 volt, it will get triggered. Okay. So if we see this, now I will plot the output. This is my output. Okay. This is not visible. Now is it visible? So now is the input visible? This is my input. This is my output. Okay. So now let us zoom in here. Okay. Let me zoom in for one part. Okay. So when you see it is crossing minus 6 volt, it is changing. It is going from minus V supply to plus V supply. And when it is crossing 6 volt, it is changing from plus V supply to minus V supply. Okay, so in this way, your inverting Schmitt trigger, you're able to see it work. Okay, you're able to see it work. There could be other ways as well. Okay. So if you see, I've placed a grid. Okay, there's a grid now. Now at around 6 volt, when it is crossing 6 volt, you see it is changing. Okay, so when it's crossing plus 6 volt, it is changing. And it is crossing minus 6 volt, it is changing again. So in this way, you are able to see that my inverting Schmitt trigger is working. So any queries in this? कुछ doubt है इसमें? Okay, so this way you can verify like there's something useful to check and to understand, like if you will be doing projects, okay, then you have to do these simulations, etc. and show. I don't know, like, so which softwares are used in your colleges? Like, कौन सा सॉफ्टवेयर आपका कॉलेज में यूज होता है? Oh, it's fine, it's fine. This is interesting. So like, no, like I'm asking, like, which software do you guys use in your colleges, etc.? You can learn. So this is for the inverting Schmitt trigger. Let me show for the non-inverting Schmitt trigger. Close this. And my non-inverting Schmitt trigger. So this is my non-inverting Schmitt trigger. And for non-inverting Schmitt trigger, what is the condition is non-inverting Schmitt trigger, the trigger point is V supply into R1 by R2. Okay. Okay. Okay, so spice is used in a lot of industry. So that's why I'm just showing it to you. If you want, you can use. If you don't want, you cannot use. But this is something good. So trigger point is V supply into R1 by R2. What is my R1? R1 is 10K. My R2 is 60K. So it is 12 into 10K upon 60K. So that is 12 by 6. So that is 2 volt. So at plus 2 volt and at minus 2 volt, it will get triggered. Okay. So let us see in our simulation. Let make it 5 milliseconds. Okay. Let me run it now. This is my input and this is my output. Okay. So if you see at 2 volt, it is changing. At 2 volt, it is becoming plus V supply. At minus 2 volt, it is becoming minus V supply. So you're able to actually get the wave. Okay. So now you have converted a sine wave into a digital wave with the same frequency. Okay. Let us change, instead of sine wave, let us use a, okay, there are very few options are there. There are few options. It is not easy to change over here. So let us change, instead we will change this. R1 is 10K. Let us make it 30K. If R1 becomes 30K, what will be my this? So this will be 30K upon 60K. So that means my trigger point should then become plus 6 volt and minus 6 volt. Okay. So let us check. So I run it again. Now if you see at 6 volt, it is changing. And at minus 6 volt, it is changing. Okay. So now you are actually, what you studied, you're able to see it clearly. And you guys know, right? Like my diagrams are very bad. And also I was thinking like, because my diagrams are bad, you may not be able to understand, etc. So that's why I just added these things, something like this. Okay, so it is better, easy to understand. Then, there's some things. So later on, maybe probably I can add some things about noise, etc. so that you can see the actual power of Schmitt trigger circuit. Probably in the next week, if I get time, I can check for the other case studies, and I could also just show you some demonstrations. Okay. So I hope this was a good thing for you. You could understand this. So if you have any doubts about this also, you can ask me and all. All right. So I'll just give a recap what we did today. So first, week 8, we want to understand what is the frequency, how we measure frequency. So I used like a digital signal. The edges are counted. We can use that. Also, we had studied T flip-flop. We understand they are edge triggered. And using that, we can use it as a counter and we can count it. So one main point is it has to be reset. It has to be reset to 0. The counter should be reset to 0. Otherwise, if it is at 5 and I start counting, then at the end of it, it will show 25. But actually, it should have shown 20. Okay, so such things to make sure, we have to make sure that a counter is at 0. Then I will start counting. And I will count only for the time which I wanted to count. Okay, that is known as my gate time. And that gate time is usually the time period of your input signal. Okay. No, not sorry. It's not a time period of your input signal. Gate time is a time you know. It should be some value which is easy for you to compute. Say if it is 1 second, I know that it will be my frequency will be equal to the number of counts in that gate time. This 0.5 second, then I have to do some addition or I have to do some multiplication or division. Okay. So that's the gate time. So first I have to reset it, and then I should enable it for the gate time, and then the input signal I must do. So these all were valid only for digital signals. But when it becomes a sine wave, then we have to do some processing. We have to do some manipulation, and we have to get it. And one way is a comparator. But in the comparator, there's a problem of noise. Okay, that problem of noise can be overcome using a Schmitt trigger. So it has an upper band and a lower band. And from that, we get a digital signal. And that also I showed in LTSpice. Although I couldn't show the noise problem, I couldn't show. But that I'll look into it whether I can add that in further lectures. Okay. Then we saw Schmitt trigger, how positive feedback is something should be there. And then this expression, which is important. That's why I derived it, how it is derived. Okay, so the thing is, you don't need to remember expressions. You need to learn how to derive it on your own. So in the exam, because you will have lots of topics to study, and as also Abhishek Chatterjee sir always encourages you not to mug up, not to remember formulas, not to like to put store information in your head. It should be like you look at the question, you get a brief idea that okay, it is a Schmitt trigger, and then you should be able to sort of derive the expression. So it becomes easier, okay, and more fun, more interesting. But also you must learn to derive fast so that you can save time. That's one part. Okay. So then there are some upper trigger points and a lower trigger point. We also showed that in our in the thing. Okay, how it is changing, when it is changing, etc. That also is visible. There's a non-inverting Schmitt trigger. Like what is the characteristics of the Schmitt trigger also I touched upon. It is similar to the BH curve of magnetic materials. Then for frequency measurement, we have a gate time and we find how many times the input signal has been triggered. Okay, that I can use to estimate the frequency. That is one way. But if the input frequency is very slow, very low frequency, means it is takes a lot of time. Then if I use this method, it will take a long amount of time. Okay. So then I use something known as reciprocal counting. For the time period of my signal, I will count a faster reference signal. That is this clock. This is my clock. Okay. And then from that, I will get my signal frequency. Okay. So this way I can get like in 1 second I can get, but in the earlier case, I might have to wait for 10 seconds if I do direct counting. So it is more faster. Then we did some sums. So this is hysteresis band positive feedback. This is not exactly the same circuit as Sir used because there's some additional resistors are there and this V input comes. So this makes it a bit more complicated. So what I did, I made one terminal as V input positive, another terminal as V input minus. I derived the expression of Vn and Vp. Then I derived the expression of Vp minus Vn. And then I use these conditions. This condition I used. Then I got the first point. I use the next condition. Then I got a second point. Okay, and then what it is, this is the band. Okay, this is the band which we had to find, and that came out to be 4 volts. Okay. Then we had a sum about digital frequency meter. So reciprocal counting. So then we could find what is the frequency of the signal using that method. Then when should we use reciprocal counting mode is there in one question. Then when there's a direct counting, the error which happens, okay, the error which happens. True frequency is 33 hertz, but I cannot actually measure it. It can either show 32 hertz or 34 hertz. So the frequency error is 1, and then I get my percentage relative error. Okay. So that's why if I want to reduce the error, what I should do? I should increase the gate time. I should increase the gate time if I want to reduce the error. But if I increase the gate time, what will happen? The time for computation, the time for it to calculate the frequency is more. Okay, so that's why that's a problem. Next, we touched about this where we found the upper trigger point, lower trigger point, and the band. And then we did this sum where we again found the same things. And then I did an LTSpice demonstration. Okay. So we will end this session. Okay. Thank you for joining.